Today I want to talk about eutrophication. Well, this is a topic we've mentioned a couple of different occasions throughout the course, but I want to go into more details today about how it's caused, how it works, and what its impacts are. So let's get to it. So, uh, Pretty simply, eutrophication is when you've got excess nutrients being deposited into an aquatic ecosystem. Could be freshwater, could be saltwater, doesn't matter. And when I say nutrients, I don't mean the stuff that I take to the gym when I get really swole. No, I'm talking about stuff like phosphorus, and also nitrogen. Remember, phosphorus is limited in freshwater ecosystems, and nitrogen is the limited nutrient in saltwater ecosystems. So let's break it down a little bit more specifically. How does this actually work? So first thing that happens is you've got those excess nutrients are deposited in the aquatic ecosystem, and that leads to an algal bloom, which is basically a fancy way of saying that a lot of algae grows really, really fast. And where does those excess nutrients come from? It can come from runoff from agriculture, from suburban lawns, from golf courses, but it could also come from the depositing or pollution of wastewater, sewage water. It could be treated, it could be untreated, but it can still deposit excess nutrients in an aquatic ecosystem. And that's going to lead to this algal bloom where you've got a lot of algae growing very quickly. And the algae is going to do two things. First thing it's going to do is it's going to block out the sun from reaching the bottom, the benthic zone, making it difficult for plants to grow. Second thing it's going to do is it's going to die eventually. The algae is going to die. And when it dies, rip in peace, the algae is going to get decomposed, as all dead things do. I personally, myself, when I die, I'm going to have my body composted. Not sure why I told you that, but anyway, moving on. These microbes are going to digest the algae. It could be bacteria, it could be worms and other decomposers, but in order to do that, they need to do a combustion reaction, cellular respiration. That's what decomposition is all about. And that requires two things: organic matter, which in this case is the algae, and oxygen. So if you've got a lot of algae that have died, now you've got a lot of decomposition going on, that's going to require a lot of oxygen. So we say there's a high biological oxygen demand. Ultimately, that's going to severely reduce the dissolved oxygen in the aquatic ecosystem, which is going to create what we call a hypoxic ecosystem. Hypoxic just means that it's very low oxygen levels, or in some cases, no oxygen levels. That's not a good place to be. It's very difficult to live without oxygen. I wouldn't recommend trying it, but it can lead to severe development, brain damage, amongst other things. And eventually, of course, any animals that rely on oxygen are going to die. Fish, namely, especially large fish, which require lots of oxygen. So this is a breakdown of eutrophication. Let's see how it looks in a beautiful infographic. A lot of words on this. Take a few seconds to take it in. We're going to start right here. Boom. Nitrogen, phosphorus. Maybe it's coming from treated wastewater. Maybe it's coming from agricultural runoff. Either way, these nutrients are going to get deposited in this ecosystem, aquatic ecosystem, and cause a bloom in algae, or also known as phytoplankton. Same thing. These algae are going to block out the sun, but they're also going to die, as all things do. And when they die, I forgot to do my numbers. Whoops. The algae bloom, and then they die, and then they decay. And that decaying process, the decomposition, requires oxygen. It's going to reduce the oxygen availability in that ecosystem, which is going to make it difficult for organisms to live there and damage and destroy the habitat, which is also going to impact the food sources of, say, any humans that rely on that habitat, but also any organisms that live in or nearby it are now no longer going to have their food source, whether it's the fish that are dying from suffocation or the algae themselves. Eutrophication doesn't just happen in freshwater ecosystems where phosphorus is limited. It can happen in saltwater ecosystems where nitrogen is limited. And these can create what are called dead zones, or extreme hypoxic zones. This is the watershed of the Mississippi River. Absolutely massive. Covers, at least a third of the United States, maybe more. All of the runoff from these farms in green and these cities in red, all that runoff of nutrients is going to end up deposited in the Gulf of Mexico, south of New Orleans and Louisiana, and it's going to lead to massive nutrient pollution outside of Houston, Louisiana, which is going to lead to a massive algal bloom and eutrophication, ultimately leading to very low dissolved oxygen and a hypoxic zone, a place where it's impossible for things to live, which is why they call them a dead zone. Here's a map showing dead zones around the world. Whoops. This is an overwhelming infographic that I'm going to break down for you, showing where do these nutrient pollutants come from. All the stuff that's getting dumped in the water leading to eutrophication, well, it can come from a variety of places. It could come from sewage, whether it's treated or untreated, will have nitrogen and phosphorus in it. It could be coming from, that's right, soap and laundry detergent often have phosphorus in it, especially the really strong stuff that you used to like wash your car or whatever. Combustion reactions. Fossil fuels we know create nitrous oxides, which can dissolve into the water and increase nitrogen. Fertilizer and manure from agricultural and feedlots can deposit nitrogen and phosphorus into the water as well. And runoff in general from parking lots, suburbs, golf courses can increase nutrient pollution. These are all different sources of the nutrients that lead to eutrophication. Something important to note is that there are eutrophic waterways, but there are also things called mesotrophic and oligotrophic waterways. Eutrophic waterways have very high algae content, high nutrient pollution, and low dissolved oxygen. Oligotrophic waterways are the opposite. They're what you think of when you think of a nice, pristine summer lake. It's got low nutrient levels. It's got low, stable algae populations, which means it's got higher dissolved oxygen. The water's clear. It's not so turbid. The fish can survive easier, so it's going to have bigger fish. This is a place you want to go swimming. On the other hand, eutrophic waters, they have high nutrient pollution, which means unstable, high algae populations, which means low dissolved oxygen, less water clarity or higher turbidity, which is going to make it difficult for large fish to survive. This is not the type of place you want to swim in. Not to mention the algae is blocking out the sun, making it harder for plants underneath to photosynthesize and survive. So keep that in mind. There are two oligotrophic and eutrophic waterways. Now, last main thing I want to talk about, it's pretty important, is this idea of dissolved oxygen in the water. When the microbes digest the dead algae, they need oxygen to do that. I mentioned that already, but you really got to get that point straight in your head, right? The decomposition requires oxygen, which is going to increase the demand for oxygen. It's going to increase what we call the biological oxygen demand. And you can see that as biological oxygen demand goes up, the water quality goes down because there's more decomposition, which means that there's a higher chance of hypoxia and organic tissue that is being decomposed. It's going to be very turbid and very gross. So let's break this relationship down a little bit and see if we can't figure out how exactly this works. Where is biological oxygen demand the highest? Well, it's going to be high in areas where there's lots of decomposition. That's this orange phrase right here. Well, where is there lots of decomposition? Well, we just learned there's lots of decomposition in areas where there's lots of algae. And where is there lots of algae? Well, we're going right back to the beginning, in areas where there's lots of nutrient pollution, which means as you get further away from the nutrient pollution, the biological oxygen demand is going to decrease. That makes sense. The closer you are to a source of pollution, the worse it's going to be. The worse the water quality is going to be. The worse the eutrophication is going to be. And like any interesting relationship in science, we can graph it into something called the oxygen sag curve, which can be a little complicated. So I'm going to use all of my skills, all of my energy as an educator, and all of my artistry as a PowerPoint connoisseur to break the oxygen sag curve down for you. Here we go. I got a river. Boom. Look at that. Beautiful river. Look at the shape. Look at the curves. Don't you want to jump in fresh, clean water? Can't wait to swim in it. But oh no. Someone's starting to dump treated wastewater in here. How could they? And the river's flowing this way, so all of those nutrients are going to start coming out of the pipe, and as they flow down the river, they're going to start dissipating. It's important to note, most of the nutrients are concentrated where near the pipe is, and as you go further away, the nutrients start to diffuse and get used up and start to dissipate, right? So we think about where is algae going to grow? Well, we're going to see the most algae grow where there's lots of nutrients, and the least algae grow where there's less nutrients, which I've represented by these translucent shapes. Not really sure what they are, but you can see I've got a solid shape where there's lots of nutrients for lots of algae, and I've got a translucent shape where there's less nutrients for less algal blooms. All right, so that's our river. We've got a lot of algae towards the pipe where the pollutants are being deposited and less downstream. Let's see if we can turn this into a graph. On my x-axis, I've got the distance from the pollution source, this pipe. And on my y-axis, I've got the biological oxygen demand, a proxy for decomposition. How much decomposition is happening? That's going to be in red. So let's put some values on our x-axis here. Here we can qualify as upstream of the pipe. Here we can actually qualify as the source of the pipe. And way down here, we're going to say this is pretty far. The further you go down, the more downstream you are of the source. Upstream of the pipe, is there any decomposition? Is there any oxygen demand? No. So BOD is going to be pretty low. But the second we get to this source, we see lots of algae, which means lots of decomposition, baby. Oh, yeah. So this oxygen demand is going to go way up. But as we get further and further away, the amount of algae goes down, and the demand for oxygen will go down because decomposition will go down, until ultimately we're far enough away that they've returned to the levels they were upstream of the pipe. Okay, let's now graph the oxygen. How much oxygen is in this water? How much dissolved oxygen is there? Well, there's no demand for it upstream, so dissolved oxygen in purple is going to be pretty high. But the second we get to the source of the pollutants, there's going to be some decomposition, and there's going to be demand for oxygen. So oxygen is going to start to decrease. In fact, the demand for oxygen is going to continue to be higher than usual, meaning because decomposition is still going on, so the oxygen is going to continue to dip. But ultimately, as oxygen demand and decomposition returns to normal, so will the dissolved oxygen levels if you get further enough away from the source of the pollutant, right? This purple curve is the sag curve. So appropriately and must I say disgustingly named the sag curve. Just don't like that word, not sure why. But you can see it's got a sag in the middle, which is why they call it that. Now we can break this graph down into a couple of different distinct categories with these dotted lines here. Everything upstream of the point source is what's referred to as clean water. It's a very technical term. I'm sure you probably don't understand what clean water is. I'm being totally facetious and condescending right now. This water is totally clean and unaffected. Lots of things can live here. But once we get to the source of pollution, this is where decomposition is going to start happening, and the only organisms that can survive here are going to be things that can tolerate higher levels of pollution and lower levels of dissolved oxygen. If we go into the next zone, which we call the septic zone, which is so appropriately named because there is so little oxygen, so much hypoxia, so much decomposition and organic matter. It's brown, it's muddy, it's gross, it's turbid. You can't see, you don't want to step in it. It goes in between your toes, it's gross. Nothing can survive here. Totally hypoxic. No oxygen. Then we get into the recovery zone where things start to return back to normal, and the oxygen is starting to go back up. Decomposition is almost at normal levels. So some organisms can live here that are tolerant of pollutants until ultimately we're farther enough away where we're back where we started, upstream of the pipe with clean water. Beautiful. Mwah! I love it. This is a complicated graph, so I urge you to watch this segment of the video a few times to help you break it down. But I've got another image here. This is a 3D rendering. I did not draw this. I know you probably think I did because of my artistry, but I didn't draw it. Here you can see the source of nutrient pollution. Upstream of the river, biological oxygen demand in red is low. Once we get to the source of pollution, oxygen demand goes up. Decomposition is high. And as we get further away, there's less nutrients, so there's less decomposition and less demand for oxygen. In the areas where oxygen demand is high, the actual amount of oxygen dissolved in the water is going to start to decrease. You might be wondering, why is oxygen not the lowest right next to the pipe? Why is it lowest a little bit away from the pipe? And to understand that, I'm going to show you one last image of this graph. This is a 2D rendering. Same thing, right? This is upstream. This is the source of the pollutant right here. You can see the pipe. And here's the oxygen sag curve in orange. Kind of hard to see, but it's there. What I want you to pay attention to is this red box here. If this is the pipe discharging the water, take a look at the concentration and the density of the nutrient pollutants. It's actually in the septic zone, a little bit further away from the pipe, where they're still pretty dense, but also very evenly distributed. So this is going to be where the oxygen demand is highest, or it's not highest, but still pretty high, but at this point, decomposition is occurring pretty rapidly. and the actual dissolved oxygen is going to be lowest. So there's actually a little bit of a lag here because the pollutants have to diffuse and disperse across the diameter of the waterway. So although decomposition is highest here, there is a sort of a lag period as the dissolved oxygen decreases and hits rock bottom in the septic zone a little bit further away from where the pipe actually is discharging. So just keep that in mind. All right, you might be wondering, I'm thinking about the Gulf of Mexico, thinking about these rivers and stuff. What can I do to help? Well, there are a couple things you can do to help prevent and mitigate eutrophication. First of all, think back to the phosphates found in your laundry detergent, in your car washing detergents, in your dishwashing detergent, your soaps. Make smart choices that have low phosphates. Furthermore, when you wash your car, do it at a car wash where they will collect and dispose of the soaps that you use, rather than doing it in the driveway where it will go down the sewage drain and get dumped into some waterway. And lastly, you can build things like rain gardens, and which will help filter and catch these nutrient pollutants and put them to good use in your yard rather than running off down the street and ending up in the waterways. And along rivers, do what you can, whatever's in your power, to help preserve these buffer zones along riparian ecosystems. Riparian ecosystems are river ecosystems. These buffer zones will do the same thing as the rain gardens, help trap runoff and help prevent those nutrient pollutants like nitrogen and phosphates from entering the water, leading to eutrophication. Anyway, that's all I got for you. If you got more questions on eutrophication, write them down, bring them to class. We'll go through the SAG curve again in person, and I'll see you next time. Bye.